you very much for the kind presentation, for the kind introduction. Hello, everybody. My name is Samet Tonyali. I'm an assistant professor in the Department of Software Engineering at Gumushane University in Turkey. Today, I'm going to talk about a password manager for the post-quantum era. I mean, let's say quantum resistant instead of post-quantum, because in the last post-quantum cryptographic conference, the first takeaway was to call it quantum resistant instead of post-quantum, because there was an impression that it's not the topic of today, it's the topic of the oncoming years. Actually, it's not, because of the reasons that I will talk about in the following slides. So we wanted to develop a cloud-based password manager using some quantum-resistant protocols. But from the schedule of the workshop, I saw that the other presentations were physics and mathematics heavy, but this time I will soften it a bit, because the software, the name indicates, it's going to be a bit more soft. Maybe you can relax, finding a while, so some time to relax and get away from all the formula and some other stuff, okay, that you see in the physics and mathematics. So, okay. This is my agenda. I will introduce the problem, motivate the our study, why we wanted to do this study, and why we wanted to use quantum-resistant algorithms. And then I will summarize what we did and why we did. Then, since it's a software, it's going to be a desktop application, and we use some really cool technology, web technologies, to develop this application, because it connects to the internet and access a cloud to store some encrypted passwords. Okay, and I'm going to give some details about the password managers and all the protocols that we use to securely communicate these passwords. So to do that, we use key exchange protocols and digital signature mechanisms. I'm going to introduce them as well. And what are our contributions with this work? Some experiment results, not very comprehensive experiments, but I will share some results with you. And I'm going to talk about advantages and disadvantages of the desktop application that we developed. Finally, I will conclude the presentation. So let's go back to the times, the World War II, and I guess you all have heard of the Enigma machine and the Alan Turing and his colleagues worked on a computer system to break this machine, because Germans were using this Enigma machine to encrypt their messages among the soldiers. Okay, so finally they found a way to break all these messages using some cryptanalysis techniques, and they managed to crack the machine. And a similar situation is just before us right now. I mean, because quantum computers are being I mean, there is some ongoing research to make them scalable. I mean, increase the number of qubits that are used in a quantum processor. For now, it may seem that they are not able to be threatful to the cryptographic algorithms that we use today. But for example, the most sophisticated one managed to crack, I mean, factorize number 15 the last time. I mean, I don't know if they have improved it since then, but that was the most sophisticated number. I mean, the highest number that they managed to factorize. But it's promising. Still, there's some comprehensive work on it, and they are trying to improve the hardware to make it scalable. And finally, one day, the researchers and some people from the industry say that they will be scalable, and that means uh, they will be able to a threat to the cryptographic algorithms that we use today to make our communication secure on the internet. Those modern cryptographic algorithms that we use today depend on the harness of two main problems. I mean, um, actually, almost all FIPS certified algorithms depend on these problems, these two mathematical problems. The first one is the prime factorization problem. For example, RSA, reverse Shamar, Adelman, and RSA PSS, this is the digital signature algorithm. They depend on the prime factorization problem. And on the other hand, the key exchange protocol that we use, which is based on the Diffie-Hellman key exchange protocol and its variants like the elliptic curve, Diffie-Hellman, etc., those depend on the discrete logarithm problem. And both problems are vulnerable to quantum computers. Especially, I mean, uh, using Shor's algorithm on a quantum computer makes it a threat to these problems because they can um, solve these problems. I mean, the algorithm can solve these problems in polynomial or near polynomial time. So, as I said, it makes the algorithm a threat to these modern cryptographic algorithms. So the algorithm consists of quantum part, quantum computer related part, and current, I mean, classical computer part. And in case the quantum computers are made scalable, there will be it's going to be a threat to the modern cryptographic algorithms. So the first problem is about the key exchange algorithms. I mean, we use these algorithms to exchange some um, secret keys to encrypt the messages going back and forth between a client and a server. And in order to make it authenticated, we use digital signature algorithms. And similarly, the algorithm, the Shor's algorithm threatens the digital signature algorithms as well, because most digital signature algorithms, again, depend on one or either of these mathematical problems. So, okay, this is the problem. We face this problem, and some people wanted to do some things like the United States National Institute of Standards and Technology. They wanted to standardize some quantum resistant algorithms as they did for the AES, because they initiated a kind of contest to determine the most eligible algorithm for symmetric encryption. Then they decided to use AES 128, 192, and AES 256. So similarly, they initiated another contest or competition to determine the standards for quantum resistant algorithms in 2017, and now it's at the fourth round. They decided, or they chose to standardize Kuiper algorithm as the key exchange protocol, and Dilithium, Falcon, and Sphinx as the digital signature algorithm. So with this work, we wanted to evaluate the performance of these algorithms on a real-world application, and we wanted to make it reasonable and it should make sense. I mean, when we apply this to a problem or to an application, it should be, we wanted it to be a good practice uh, to be used in real world. Kind of, we wanted to have or come up with a kind of prototype that can be improved later and used as this. Anyway, so we developed a desktop application, a password manager, and this password manager used those some of those algorithms, and we evaluated the performance, like the key exchange, how much time it took, and some other metrics. And we wanted to see if it's really viable or not. In this way, we wanted to provide some insights. Anyway, so we developed a password manager as a desktop application. It's cloud-based. It connects to the internet and store the encrypted passwords on the cloud. So if the user um, formats its machine, or I mean, kind of lost its connection to his laptop or desktop, whatever, he can download the application and logs in, then continues to use the application, the password manager. So we wanted to do this. Otherwise, if it's stored on the computer, if it's an offline application, it means it will be used only on the desk, on the machine. If the access to the machine is lost, then all the passwords are gone. We wanted to thwart that, avoid that, to make it a cloud-based application. But it's running on the desktop. So the application that we developed is responsible for the encryption and decryption operations, because we cannot let any other party to reveal the real password of the user. So if the user downloads their passwords from the cloud, they need to reveal or decrypt the encrypted passwords on the client, on the machine. And right after they use these passwords and usernames, whatever, okay, so they discard them and they don't keep it on the memory, because some kind of malicious software can get into the memory blocks and retrieve the original password. So in order to avoid that problem, that attack, we just use, I mean, the application uses or populates the input fields on the browser with the data, with the required username, password data, then they are discarded. They they are not kept in the memory. Okay. So in this way, so we store the encrypted passwords on the server. Thus, we make sure that no one can reveal the original password, even if they compromise the server. Okay. The only thing or only stuff they will find is the encrypted versions of the passwords. And how we encrypt them, we use some passphrases. So a passphrase is different than a password. A password is typically 10 or 16 characters, but a passphrase must be a bit longer. And it's not necessarily to be some combination of characters, uppercase character letters, lowercase letters, spatial. You can use some lyrics if you want, or some statement that you love, but it must be a bit longer. And this is the only thing that you need to remember. The other parts will be stored on the cloud in an encrypted form. Okay, so this is what we call the on-the-fly key generation. So we provide the passphrase and it's used as an input to the key derivation functions, and this function generates the key that we use to encrypt the passwords. And once the passwords are encrypted, they can be communicated to the server. And during this communication, we use another layer of security because uh, um, this is because there are some malicious parties that can eavesdrop the communications, regardless of the medium. I mean, it can be wired or wireless. They can do that. And some technical details. The JavaScript object notation web tokens are used to perform authentication and authorization between the client and the proxy server. We use a proxy server as a kind of good practice because sometimes we may need to implement some other precautions for, like, I mean, SSL investigations and some other stuff. We do not implement very complicated structure in the proxy server for the study, but it's a good practice. So that's why we wanted to have a proxy server. I'm going to show you the general overview of the protocol in the following slides. Okay, so, and of course, we use the quantum resistant key encapsulation mechanisms and digital signatures for authenticated key exchange. Since this is a software, I wanted to give some information about the web technologies that we use when we develop this application. First of all, we wanted to carefully choose the technologies that we're going to use because we wanted it to be as performant as possible. Because, of course, it's not going to be ready to use on or I would say ready to use by the people, but we wanted it to be performant. I mean, reactive as possible. So we use JavaScript and TypeScript at the front end and back end. Why we wanted to use TypeScript? Because it enables us to catch errors in compile time instead of running time. And we used Electron. It's a framework to develop desktop applications using HTML, CSS, and JavaScript. It includes a kind of embedded Chrome, a Chromium project, which is used to develop the Google Chrome today. And in that way, sorry about that. So in that way, we were able to use the HTML, CSS, and JavaScript to develop a desktop application. Because these are the technologies, or I mean, markup languages that we use on the browsers rather than desktop applications. Anyway, and this Electron framework is the framework that is used to develop Discord, Twitch, Facebook Messenger, and WhatsApp Messenger on a desktop. And we also use the React.js. This is the leading front-end library, which was developed by Meta. Facebook, or it was called Facebook, but now it's Meta. And we use that to develop the front end of the application. Okay, and Node.js, there was supposed to be an E after D. Okay, Node.js, this is the library that we use to develop the backend side. Okay, it's also a JavaScript code. Typically, we use JavaScript for the front end, but Node.js library allows us to use JavaScript at the backend side. Okay, and in that way, it improves the interoperability of the front end and the backend because they use the same language. Express.js, it's a framework to develop the REST APIs because there will be some API endpoints to request some resources from the server, and those resources are made public using the Express.js. It's an intuitive way to build fully equipped API endpoints, and the server and the proxy written, I mean, the server and the proxy server were written using this framework. And as a database, we use MongoDB because it's easily configurable document-based database. Tailwind CSS, as the name indicates, it's a CSS framework. We used it to style the application, make it a little bit fancy. And Chakra UI, it was used to create performance models. And we developed the application on a Linux development environment because there's a ready-to-use library to from which we can retrieve the some instances of quantum-resistant algorithms. liboqs library. It's a quantum safe, open quantum safe project. Okay, so it's a product of or an output of open quantum safe project. So we use that library to make the quantum resistant algorithms in our application. So this is the general overview of our application and the cloud side. So before the passwords are retrieved and transmitted to the client, a secure key must be established between the client, this desktop application and the server. Okay, turn this off. Okay. So here we used for the key exchange or key encapsulation, Kyber 512, and the Lithium 2 for digital signatures. And let me explain what's happening here. So upon the user login, user logs into the application and the client sends a request to the proxy server, which then engages in the key exchange with the server and replies to the client with the shared script, which is used for subsequent communications. So as the name indicates, it's a proxy server. Okay, so it's in the middle of the road from client to the server, and client talks to the proxy server, and proxy talks to the server on the client's behalf, and they establish a secret key. Then after that point, they use this secret key to send messages back and forth. In this way, even if there's a eavesdropper in the system, they cannot reveal the original messages because they all will be encrypted using this key. And the key encapsulation mechanism that we use here, the Kyber, is both resistant against quantum computers or quantum attacks and classical attacks. That's why we can use them alone and also in a hybrid fashion. What I mean is we can use them another classical key exchange algorithm like Kyber can be used with Diffie-Hellman, for example, using some specific curves. At least we can make sure if any kind of vulnerability is disclosed for the quantum resistant algorithms, at least we will have the classical key exchange algorithm safety or the security. And the same applies to the digital signatures as well. We can use the Lithium, some other classical digital signature algorithms. Anyway, so specifically during the key exchange, the proxy server generates a public key and signs this public key using the its own private key. And sends this signed public key to the server. And server first needs to verify the signature. Once everything is okay, if the signature is valid, then the server generates a secret key and encapsulates it using the key encapsulation mechanism, the Kyber, and sends the ciphertext, which includes the original secret, to the proxy server. And proxy server hands this to the client. And the client, in a secure way, of course, and the client uses this key to encrypt the messages that it's going to send to the server. And server decrypts the messages coming from the client using that key and encrypts any message it wants to send the client using the same key. So at the first stage, it's the public key cryptography. The sites use their public-private key pairs to establish a secret key. Once they determine that secret key, both sides have the same secret key, they start using symmetric key encryptions. So they use the same key to encrypt and decrypt the messages. And this is called the symmetric key. Okay, and the point is the server receives the encrypted passwords of the client's passwords, but they are encrypted using a key that was derived from the passphrase given by the user. That's another encryption. On top of that encryption, they use the Kyber algorithm to exchange another key to conceal or the encrypt the messages that are going to go back and forth between client and server. In that way, we put another layer of security on these messages. At the server side, it decrypts the messages coming from client, but it reveals only the encrypted passwords. And that or those encrypted passwords were generated or were encrypted by a key that was derived from a passphrase that's known by the client only, the user. So that encryption part, the first encryption part was carried out on the client. Then a new key was established between client and server to conceal, to secure the communication between client and server. And in that way, we managed to keep the eavesdroppers away from our communication. They can only get some encrypted messages. And since at every session we use different keys, they will not have sufficient number of messages to apply some cryptanalysis algorithms. And by the way, you can ask a question here. What about the quantum computers? What about the Shor's algorithm or Grover's algorithm? According to NIST, if we use symmetric encryption and if we keep the key in the size of the key a bit longer, or if we double the size of the key, we are fine. We are okay. They claim that. The standardization process deals with only the public key cryptographic part. They say, okay, if you double the size of the key that you use for the symmetric operations, you are fine, you are okay, you're secure. Otherwise, on the public key cryptography side, you need to come up with some new algorithms that are not depending upon these two problems. Prime factorization problem and discrete logarithm problem. Anyway, this is the general overview of the applications, how the application works. Okay. So the contributions, our contributions, first of all, this is the first try of using quantum resistant algorithms with a password manager. It's not a real application, but pseudo real or pseudo production environment, we call it. And standardization process is still ongoing, but we wanted to use these applications on these algorithms on such an application. So we wanted to see how it performs, and the encryption, decryption part, and the signature verification, signature generation parts. So, and also we implemented the application in a way that the server is kept completely out of the loop. In that way, um, those passwords can be securely stored on a cloud-based, on a database, on a remote database running on a cloud. Okay. In that way, we ensure that in case of any kind of compromise, I mean, server or database compromise, the passwords will be kept secure, because the only stuff that the attackers will find will be the encrypted versions of the passwords, original passwords. So we performed some experiments using a computer with an Intel i5-7300 HQ processor, and it was running Ubuntu 20.04 on a virtual machine. So the key encapsulation time took 92 milliseconds. Decapsulation time took only 0.90 millisecond. Encapsulated key size is 32 bytes, and digital signature generation time is 22 milliseconds, and verification time is 190 milliseconds. It's a bit higher than the generation time, and the digital signature size is 2,420 bytes. And now some results. The key encapsulation and decapsulation is in acceptable limits. They don't take too much time. The signature generation and verification takes more time, but still acceptable. Compared to the encapsulated key size, digital signature is much larger. So this brings a bit overhead, and we need to have some space in the bandwidth to accommodate some other traffic as well, of course. And this might be a kind of problem maybe, because it increases the size of the message that we are gonna transmit on the network. And we can say in general, the algorithms are viable in production environment, but we know that NIST has initiated another competition for digital signatures. They are looking for more efficient and less message overhead producing digital signatures, and it's still ongoing, and it's at its infancy right now. And actually, we will have some results. We have some results in case someone tries to implement such an application, such a password manager, and at least we give an insight of what they will face if they want to develop such an application. So what are the advantages? Quantum safety. It protects against attacks from the quantum computers using Shor's algorithm. And user authentication, we ensure that the multiple users coexist on a single client and they can perform separate key exchange. We powered the application using JSON web tokens and transmissions performed with a valid post-quantum or quantum-resistant key and the valid access token. This comes from the web token JSON Web Token. This is a very commonly used technique in web applications to authenticate the users. And the server is ignorant. It doesn't know anything about the original passwords. It just receives the encrypted versions of the passwords because we encrypt them using a key that's derived from a passphrase that's known by only the user. What are disadvantages? They're still susceptible to attacks that can snoop through memory. We haven't implemented this part actually. I mean, we wanted to do it that because we aim to have that property as well. But once it's incorporated into the application, it will be a good contribution actually. The main challenge that we encountered during this work was the complexity of key flows because we are using a key for actually a passphrase to derive a key, and we use this to encrypt the passwords and then establish another key between the proxy server and the client, another one between proxy server and the server, and the key flow, the complexity of key flows was, I mean, forced us to, I mean, was the most challenging part of the application. As a complex application, a multitude of keys being generated, exchanged, and stored, and the number of keys, yes, that we use in this application is a bit higher than a normal or a classical application. And as we include more keys, the complexity grows. And so we wanted to alienate this complexity by visualizing the flow before the implementation of any code. So, I mean, the design part was, I mean, took too much time to complete the work. And once all the key flows are determined, then we start to implement the application. In conclusion, we investigated the quantum computing threat in terms of a password manager, looked into how possible quantum-resistant standards perform in a production environment. We discovered that these algorithms are performant and viable and shouldn't be an issue when implemented in a production application. At the moment, it's not a very big threat, but there is an how to say, there's an approach that we call harvest now, and collect now, harvest then. I mean, some malicious people or how to say, state nations might be collecting all this traffic just because they can use Shor's algorithm or such algorithms once the quantum computers are scalable. They collect them now, then they can use some scalable quantum computers to reveal the content of these messages. They can reveal the keys first, and they can decrypt all the encrypted messages using those keys. So that's why we need to take an action right now. Okay, that's why we wanted to do this work. I mean, show kind of path to the developers and how they can apply those algorithms for a password manager. Of course, there are too many application areas that we can use those algorithms. And NIST, the National Institute of Standards and Technology, is in the process of developing new cryptographic standards for a quantum safe future. They are still looking for some candidates for digital signatures. They have just initiated that process. And now the post-quantum cryptography competition is in the fourth round. hopefully, once standards are finalized, the gradual migration to these algorithms can take place, and governments, I mean, the governments in Europe, in the United States, are publishing some mitigation plans, migration plans to migrate some quantum resistant algorithms from the classical algorithms. They, of course, want to do that with an hybrid approach first. They will use them along with the classical counterparts first, and after a while, they will go with the quantum resistant algorithms, I guess. And these are the references that we use for this study. And you can see, I mean, you can access the source codes of this application following these links. I mean, this is my undergrad student when I was an assistant professor at Abdullah University in Kayseri. So Lekan implemented this application, and these are the uh, source code for the application. And this is the server part, and this is the proxy part, and this is the uh, graphical user interface part. Anyway, that's all for this presentation. Thank you for your patience. I can take your questions if there's any.
So thank you, Professor, for a very nice talk. So I guess we have some questions from the Zoom audience. Michał, could you, yeah.
Yes. So I understand that what you addressed so far is only post-quantum resistance. That is that you make it harder to decrypt, but ultimately, since the progress of quantum computing gives the exponential speed up, we can expect that these algorithms will also already use the server to use quantum communication to prevent eavesdropping of the key and make sure that it's just challenge response. And then possibly the authentication could never be hacked.
So actually, we cannot call this a quantum communication because it's something else. We are talking about classical communication, but using quantum resistant algorithms. They are also like the classical algorithms, but we do not use any kind of quantum technology here. I mean, we don't use any quantum key distribution or something else. I mean, for example, Professor Yarek Duda mentioned the two-way computers, and as far as I understand, he claims that these computers can crack those algorithms as well. I mean, the algorithms that we call quantum resistant algorithms. In such case, there's no other choice is left but using the quantum key distribution algorithms. I mean, if I don't misunderstand you, I mean, is that the question you're asking? I mean, so we are not using the quantum communication. I mean, if there's
Yes,
some
yes,
gap here,
but you
we
still
don't.
communicate with the server. So all the communication with the server, if, for example, you have a hostile network environment and
Yeah,
you
okay,
use the yeah, then this will be stored for later, and maybe much later. You could hack the post-quantum crypto algorithm also, right? It's just harder to crack, not impossible. And it is not yet proven. So I understand that this is main issue with an NIST standardization effort is that those algorithms that were proposed not only have the relatively long key lengths, but their resistance to quantum attacks is predicated on still relatively low number of bits that quantum computers would have, and this number is growing very fast.
Yes, that's right. I mean, they are actually they are developing the algorithm and they are analyzing the algorithm and they are discussing this on some dedicated forums. I mean, they are doing their research. I mean, but from the classical approach, uh, there's nothing else to do. I mean, they need to find some other problems that they can use to drive new algorithms. I mean, this is the only thing they are doing. I mean, the problem here is they want to take action as soon as possible because all I'd say critical communications can be um, collected right now, and once the quantum computers are scalable, I mean they can compute larger uh, numbers than 15, of course. I mean because the security of the those algorithms are, of course, depending upon the key size. It changes, but I mean they have 128 or 256 bit security. But I mean once the quantum computers are scalable, they manage to do that for longer, much longer keys, or numbers. If they can factorize those kind of numbers in polynomial time using quantum computers and Shor's algorithms, it's going to be a kind of problem, because they will use that algorithm using quantum computers, and they will reveal the keys first. And because there's a key exchange protocol between the client and server, first they will reveal the key, and once they reveal the key, decrypting the encrypted traffic is not a big deal. So, is that the kind of answer to your question, or did I misunderstand?
Yes, I still think it's a little bit of unfair marketing tactic. Some fair marketing tactic would be with the previous generation of password managers, it's likely to be broken in 10 or 15 years, but with the new generation, we have 25 or 50 years, right? But I understand where you come from. So you pick the narrow topic, and it's still unknown whether PQC will be hackable or not. That's probably what hampers the standardization effort. The second question I would have is that most password managers now are integrated with the browsers, right? Or integrated with operating system. By choosing Electron, you make it maybe more difficult because you need a separate application. Would you comment on that, or do you have answers?
Actually, I use one password manager that was developed by Kaspersky, and it has an application, but if you want to use it on your browser, you need to include an add-on, or an kind of extension. Okay, so our application can be extended using such an add-on or kind of extension, because, as I said, even this Kaspersky's password manager uses extensions to communicate with the browser to populate the input fields in the forms. So this can be done, it's doable, but you need to put some effort. So this is just kind of small prototype, or some you can think it's a undergrad senior project. Okay, so he didn't put too much effort after the graduation, of course. So this was the first result. These are the first results that we get, and that's all. We published it and left it there. Maybe we should build a more useful password manager like this, because this quantum resistant algorithms will be kind of a trend after a while, even in Europe, not only in the United States. Even in Europe, the governments are publishing some migration policies, migration recommendations, how to migrate from the classical to the post-quantum. So maybe we can come up with a production environment. I mean, an application that was produced for the as a real application that can be downloaded, installed, and used in a secure way. I know that that's an opportunity that can be taken.
Michał, are you satisfied with the answer?
Yes, thank you very much.
By the way, could you make a self-introduction, because you have like camera, because we are just curious who you are. Such brilliant comments, you know. So where are you from, Michał? Hello?
So I'm from Łódź actually originally. Unfortunately, my camera doesn't seem to work.
No, works. We can see you. We can see you, right?
It does, right. So I'm from Łódź. I'm now living in Warsaw, but so that's why I'm remotely here. I got PhD in bioinformatics, master's in computer science. I worked on different blockchain technologies and in few financial institutions. Currently, I work for MediaMake.com, the company I founded. I'm very interested in post-quantum cryptography because of involvement in blockchain. But I also am interested in general science involved. So I recently published, actually it's still in review, work on ultra-affinities logic that shows how Gödel's uncomputability assumptions are wrongly made. So we can make sufficiently powerful logic that is decidable. I also worked on different kinds of AI tools or AI-like tools for automatically inferring types for JSON or for creating libraries, software libraries from documentation web pages, this kind of stuff.
I see. What's your last name, if I may ask? What's your last name?
Gajda, G-H-A-D-A.
Oh, right. Sounds
so
good.
I may post the company site, but unfortunately chat is limited to only Bureau, so I cannot just widely post it to everybody.
I see. All right.
You would have to repost it to everybody if somebody is interested.
I will send my emails later, I guess. Right. So thanks very much for very brilliant comments and sort of introduction. So do we have more questions? Yes. So there is one question from here.
Okay. Oh, by the way, Michał, I don't want to go into discussion between people who are actually commenting only.
Maybe make also self-introduction.
Yes, my name is Mirek, and I am chairman of the University Council for this university where Krzysztof is working now, and I also have a quantum blockchain. So Michał, go to quantumblockchains.io and contact me about this post-quantum. We can discuss that in the blockchain context. You can also download my white paper and see what we've done in that space. I think there are maybe interesting things to discuss. But my question to Professor is different. You mentioned somewhere shortly, extremely shortly, the library on the slide that I saw was liboqs. It's open quantum systems, I think, this famous post-quantum implementation, right? Is that right?
Yes, that's right. It's an open quantum safe project. They developed a library, liboqs. I can actually let me open the page and I'll show you. Let me see. Okay, now I'm going to share my screen with you.
Okay.
Okay, can you see it right now?
Yes, exactly. So that's what I meant. So this is standard binary code, and I understand you interface that to your JavaScript Node.js code. So the actual implementation of Kyber and the Lithium are C++ binary codes compiled and then interfaced to these languages. Is that right?
Yeah, actually, there are some language wrappers that can be used, but Okay, let me check the links. I mean, I'm gonna check the. Just give me a second.
Well, no, that's okay. I understand that it's probably the case because if you use these, this is pure binary. That's because your timing was very good, and I was actually curious what you used, and used this original application, I believe.
So in somewhere in here, there must be a kind of link to the post-quantum part that's given, but I'm not sure. Okay, so we have the LibOQS node here.
Yeah, so you must call these algorithms. Okay.
Yeah,
Understand.
It could be a kind of wrapper over the implementation of LibOQS, but not directly.
Because it mentions also OpenSSL, so no, it's not JS wrapper. Okay, I see it clearly. Okay. So the second question is this. I mean, when you go to MongoDB finally, and you store passwords there, that's symmetric encryption, right? So you use Kyber to change keys, but the data is what kind of AES? It's AES 256, 512. What kind of blockchaining you
So we don't use blockchain here, but so here's the thing. First, we apply an encryption on the client using the key that we derive from the passphrase. Okay, and this could be the AES or Cha-Cha 20 or something like this. I don't remember it right now because it's been a while. So first, this is applied on the client side, and the server doesn't know that key because we derive it from the passphrase entered by the user. That's one encryption. Okay, we provide a kind of security layer on the password. Then we store these encrypted passwords on the server side, but while communicating these passwords, encrypted passwords, first we need to exchange a key. Then we use Kyber to establish this key. Once we share the key, then we use this key to encrypt the encrypted passwords and send to the server. Server then use the same key to decrypt them and store in the database.
Okay, yeah, that's what I was thinking. By the way, you mentioned passphrases. There is a fundamental problem with post-quantum algorithms and passphrases because for post-quantum algorithms, we need, as we know, pretty long keys. And the current passphrases taken from this world of blockchains, so you know, this famous vocabulary, which has, if I remember well, 2000 something, words.
For encryption, I mean, for the encryption part on the client, we don't use any kind of quantum resistant algorithm. We use the classical symmetric key algorithms. So we derive the key and use that key to encrypt the password in a symmetric way. I mean, we encrypt it and we decrypt it. So we encrypt it, we use another key to communicate to the server, and once we retrieve it from the server on the client, we again use that passphrase to drive the same key and then decrypt it to have the original key.
Okay, understand. Okay.
So the client both encrypts and decrypts the passwords.
Yes, okay, I understand that. That's the mechanism you use. But I was just making a remark that for post-quantum algorithms, these asymmetric algorithms, both for chems and digital signatures, there is a problem not very well solved yet, which is, passphrasing. I mean, if we go to standard asymmetric algorithms with a standard key length for elliptics and RSA and Diffie-Hellman, it's pretty easy because these passphrase generators with, say, 24 words are completely enough. For post-quantum, they are not enough because we don't have enough entropy. Just the physical, mathematical entropy is just too little, and that's a big problem, not very well solved yet. So I am happy to discuss in the future through your contacts, Krzysztof, with you, because that's something that requires many brains how to solve. I'm working on that, and I can tell you it's extremely difficult problem.
I see, but I mean, to be honest, I don't have the knowledge to discuss this because we are the applicators, kind of. I mean, the applies. The ones who apply the protocols or the algorithms on some use cases. They are the developers of these algorithms. I mean, that's why I cannot say anything about that part. I mean, you know, the entropy part. I mean, you're providing the sufficient entropy to generate some random numbers and some other stuff. I mean, I don't have the.
There's a lot of interesting things. Like, for example, in my opinion, and that's actually going a little bit toward Michał, what you said. I mean, some part of real quantum technologies could be used. For example, entropy we just mentioned could be used today without expensive quantum QKD technologies to improve these things through the mechanisms which we call quantum random number generators. They are available and not very expensive even. So that's. But we probably go over time. And thank you very much for your answers.
You're welcome.
Dialogue was great, fantastic. Thank you.